Alright gang, so today we're going to look at Chapter 5, and Chapter 5 is all about inter VLAN routing. And this is where the lines between routers and switches kind of blur, because the only way for VLANs to talk to each other on a switch is through a router. And in the old way, the way you did that is actually running two cables from the switch from the different VLANs into the router and let the router route for you. But now you can do that internally because the switch itself will act as a router to route that data. We're going to talk about that. So we'll talk about inter VLAN routing configuration. We'll talk about how to troubleshoot some VLAN routing. We'll talk about layer 3 switching, which again, remember, this is where we start talking about IP, so you've got to make sure you go back and remember all your different layers. We're going to talk about the three primary options for enabling VLAN routing. We're going to talk about legacy inter VLAN routing. Then we're going to talk about a configuration known as a router on a stick. This is a term that you'll hear a lot, and we'll talk about what that is and what it does for you. And again, basically with a small network, a router on a stick may be all you need. We'll troubleshoot some common VLANs. We'll talk about IP addressing issues with an inter VLAN. And then we'll talk about how to route with an inter VLAN and finally troubleshooting. So, okay, thinking back, layer 2 switches, which are your Ethernet, cannot forward traffic between VLANs without the assistance of a router. VLANs are designed so that layer 2 data stays completely within that VLAN for purposes of security or for setup or any of those things. So basically it's like a separate switch. VLANs are one physical device, but they act as completely logical devices, which, as you know, if switches aren't connected or if they have different subnets, the only way to route between those switches is with a router. Well, when you think about VLANs, it's easy for me to explain, but the way to remember it all is think about a VLAN as a completely separate network. Even though we're dealing with one device, think of a VLAN as a completely separate switch with all its separate commands and everything else, because that's how it's treated. So in the past, you had to have an actual router to route between the VLANs. Each VLAN was connected to a different physical interface on the router. So you would need several ports on a router if you had several VLANs you needed to route. Packets would arrive on the router through one interface and be routed to leave on another. Because the router interfaces were connected to VLANs and had an IP address for that VLAN, they were able to route it just like they would any other type of traffic. Large networks with a large number of VLANs required many router interfaces, and this is where things got tricky. Imagine needing a router with 24 ports on it because you have 24 VLANs that needed to be routed around in your company. So that just got to where it was kind of out of control. So the way to handle that is called the router on a stick approach. And basically, one of the router's physical interfaces can be configured as an 802.1q trunk port, which means it'll understand all the VLAN tags. Logical subinterfaces are created then, one for each VLAN, and each subinterface has its own IP address from the VLAN it represents. So again, you remember from our tagging last time, we're putting that Q tag on it. So all the data is going to come in separate. But since the VLAN port is configured as a trunk, it's the VLAN port on the router rather is configured as a trunk. It's able to see all of that data coming in. VLAN hosts are configured to use the subinterface address as the default gateway. So if I've got 192.168.54.1 on one VLAN and 55.1 on another, I'll put those as my gateway on the machines that are on those VLANs, and they'll be able to route through each other using that. And the key to this is only one of the router's physical interfaces are used. So you can go back to using a router that maybe just has 2 interfaces or 3 to do all of your work for you. Now here's where it gets kind of interesting. Multi-layer switches can perform layer 2 and 3 functions, replacing the need for dedicated routers. In our earlier example with router on a stick, you're still actually using a router to do the routing. But now what we're talking about is that with these multi-layer switches, they support routing themselves and inter VLAN routing. So the switch itself can act as a router. The multi-layer switch must have IP routing enabled for this to work. And a switch virtual interface is set for VLAN 1 by default. On a multi-layer switch, that can be configured for any VLAN. So basically, you're just replacing what the router does with the switch and letting the switch do it for you. Since the switch understands network layer PDUs, it can route between the virtual interfaces just as the router does between its interfaces. With a multi-layer switch, traffic is routed internal to the switch device. This process is suitable and scalable in most cases. So this is the reason this really all came about. If you think about computing and how much it's changed as far as processing power, we have bigger processors in these switches now than we've ever been able to have before because it's not as cost prohibitive as it used to be. In the old days, you didn't use very many routers because they were so dang expensive. But now these smaller switches are capable of doing everything that the old, bigger routers would do because they've got their own processors and memory and everything else. So when configuring legacy inter VLAN routing, it requires the routers to have the multiple interfaces. That's what we talked about at the first. Each one of the router's physical interfaces is connected to its own VLAN. Each interface is also configured with an IP address for that VLAN. Network devices use the router as a gateway to access the devices connected with other VLANs. You can think about legacy VLAN as being just like regular routing. If you had several switches each run into ports on a router and each switch had its own subnet, that's basically what you would do with legacy VLAN. The only difference is that they're VLANs, so they're on one physical device instead of separate physical devices. So here we've got an example of that. Notice that there are two interfaces that need to go from the switch to the router because we have two VLANs in use in this graphic. And they've got separate IP addresses. They used 172.17.10 and 1730. So there would actually be two ports in use to go to the router. And two ports on the router would be in use in a legacy setup to make this work. So here are some of the commands to actually set up the legacy. First we'd go to our VLAN, set our interface, set the switch port access on those ports that need to go there. Once we end, we'll get a system message saying it's there. Then at the end, we're going to copy the run to the startup so that it'll stay after we reboot. So here to configure the router, we're going to go to the interfaces on our router, which in this case was gigabit 0 and 1. We're going to assign them IP addresses. We're going to issue a no shutdown to keep them up. Notice as soon as we do a no shutdown, we get a couple of messages saying that we've changed the state to up on those links. And then again, we'll copy the running to the startup. All right, so the first alternative to the legacy is the router on a stick. Remember from what we just talked about, we're doing a VLAN trunk with router on a stick. So the physical interface of the router must be connected to a trunk link on the adjacent switch. On the router, you need sub-interfaces for each VLAN. So we're going to issue our commands like we do on a switch to set up our different ports on our VLAN. Each sub-interface is assigned an IP address specific to that subnet. So here in our example, VLAN 10 and 30 with two computers, now we've only got one interface or one physical cable running to our router, but it's going to have a couple of sub-interfaces. So on the router, we're going to do encapsulation to ensure that it's going to accept VLAN trunks. Assign the IP address. Go to your interface and set the two different VLANs. So first we're going to do a .1Q10 and then a .1Q30. We're going to set the IP addresses on both of those. To make life easier here, they used VLAN 10 with IP address .10 and VLAN 30 with .30. You wouldn't have to do that. It just makes life easier if you match things up. And then we'll issue a single no shutdown to the interface itself. Notice with this no shutdown, I'm going to get a couple of link ups because I've got the link itself up, and then I've got the two virtual links on that link up. So show VLANs would then show that I'm set up with that VLAN in use. And show IP route should show that those are directly connected so routing can take place between them. So the easiest way to verify that routing is working, whether you're doing legacy router on a stick or inter VLAN, is to use the ping command. Ping is just a command that sends out a request and gets a reply back from a device saying, yes, I'm there. So it uses a protocol called ICMP. When a host receives an ICMP echo request, it responds with an echo reply. Traceroute is another utility that we can use to confirm that the routing is taking place in the path that it's using. So one thing about ping that I want to point out here, though, I think it's a great command. I use it a lot to see if services on the internet are up. But Windows has gotten in the habit since they added the firewall back in, I think, XP Service Pack 2, to not reply to ICMP requests by default that are outside of its local subnet. Now, Windows Server does a little different. Server will reply, but Windows won't. Windows 8, unless you're inside that subnet, or Windows 7 or XP. And the problem with that is that if you're trying to get to your computer and you've opened ports up, or maybe for some reason you've even put your computer in a DMZ on a router, when you ping it, you're not going to get a response because you're not going to know that it's up and running. So just to make sure y'all have all seen the ping command before, I'll just ping google.com. Now I'm running IP6 here, so notice that my reply is actually an IP6 address instead of an IP4 address. I believe if I put /4, it's been a while since I've done the command, that'll make it respond with a IP4 address. So there's Google's IP4 address coming back. So basically what this means is a request is leaving my machine. It's going to www.google.com and it's saying, are you there? And it's getting that ICMP echo back that says, yes, I'm there, I'm operating. Traceroute is basically the same thing, except Traceroute is going to show all the paths that your request goes through in order to reach your destination. So here, since I didn't specify, it's going to go out as an IP6 request. So first we're going to hit my cable modem, which is this top IP6 address. And once we actually get out on Comcast, Comcast has named their IP6. So you see here is the path it's taking to reach google.com. And if I issue that same command again, I think with a /4 or a -4, up, got to put it before, I can force it to use IP4 instead of 6. So I'm going to go ahead and break this, but you get the idea. The first address is actually my router, and then the second address is the cable modem, and then it's out on the actual Comcast network so it can go out and resolve its way all the way to Google. All right, so some issues that happen when you are using the legacy routing model: ensure that the switch ports connected to the router interfaces are configured with the correct VLANs. One thing that happens most often as far as issues is that the wrong VLAN is assigned. And if the wrong VLAN is assigned and you haven't used the switch port mode trunk command, you're going to have some trouble. So here, show interfaces, show fast Ethernet, in this case 04. Switch port will show you that it is turned on. The trunking is .1Q and trunking is on. If you're going to use router on a stick, the problem that's most common is assigning the wrong VLAN ID to the sub interface. Everything's got to match up, so make sure your VLAN IDs stay the same everywhere. It's not important what VLAN you use, it's just important that you use the same VLAN. One thing that Cisco shows here, and that I think is the way to do it, if you are in complete control of your network and you're using internal IP addresses, so you're going to use non-routed, 10s or 192s or 172s, whatever, make your VLANs match up with your IP addressing. That will just make your life easier. If you know that 192.168.11. whatever is always going to be stuff on VLAN 11, that will just make it easier for you. Otherwise, you need to make yourself a good network map and make sure you keep up with it. So here, commands they're using: show interface. We're going to see that encapsulation is on. The VLAN ID is 100. The VLAN ID needed to be 10 earlier, except they changed it to show for this example. So another error that sometimes happens is that you're using an incorrect IP address and mask on the interfaces connected to the switch. So make sure that those are correct, that you've assigned an IP address to the ports, and that on the PCs themselves, make sure that they have an IP address, that it's been assigned properly. So to verify that, you can show IP interface, and then finally do a show run to look at your entire config file and make sure everything is good. So another thing that we should discuss is layer 3 switching. And layer 3 switches will usually have packet switching throughputs in the millions of packets per second. They're pretty quick at what they do. All of the Catalyst switches from Cisco support the following layer 3 interfaces. They support routed port and they support switch virtual interface. Some of the higher performance switches, like the 6500s and the 4500s, are able to perform most of the router's other functions as well. Again, this is where it gets kind of blurry because devices are able to do more than they used to based on their layer. In the old days, switches were always layer 2 devices, but now we're talking about layer 3 switches. And though not common yet, I've even seen up to layer 7 switches where these switches themselves actually perform looking into the packets and packet inspection to determine what to do with the packets themselves. Instead of just looking at ports, they actually look at content. So today's routing has become faster and cheaper and can be performed at hardware speed. In the old days, routers were expensive. They're not as expensive anymore. Now, I probably shouldn't say this because it's Cisco class. A Cisco router is still expensive, and a Cisco switch is still expensive. But nowadays, there are lots of alternatives to actually just Cisco equipment. And make sure that, you won't need this for the CCNA, but be aware of it. You may end up working somewhere that is not a Cisco shop. At BIPSI, for example, most of the switches are HP. So even though the same principles apply and the commands are almost identical, they're a little bit different because they are using HP's version of iOS instead of Cisco. Another one that I'm really familiar with is called PFSense. And pfSense is a free router that you can download. It's a version of FreeBSD that you run on a CD-ROM, or you can install it to a small hard drive, or you can even install it to like an SD card if you have a computer with an SD card in it, a CF reader. And you just put a machine with two interfaces in it, two network cards, and let it do all the routing for you. I've used pfSense in a lot of different places. I actually run it here at home. And on my little home network, I've got an old Pentium that's got 3 network cards in it. One runs out to the internet, and one runs to my local network. And then I have wireless on a separate interface so I can control what happens on my wireless. But there are alternatives like that that are cheaper and that you're likely to run into. So kind of be aware of them. So routing can be transferred to core and distribution devices with little or no impact on network performance. Basically, you can spread your routing out is what this means. You can do a lot of routing with inter VLAN and inter building, and that keeps the network from being congested where it doesn't need to be. If you think about like a college campus where things are spread out, inter VLAN routing and inter routing or switch routing is a key component, because thinking about BIPSI, for example, building F, if we can route everything inside building F that needs to go to building F, that keeps it from needing to go to computing services in G and then back to F to get routed. So things that can be routed locally will be routed locally. And then things that actually need to go out on the internet can come to your core router to be routed. So by default, a switch virtual interface is created on VLAN 1, the default VLAN. This allows for remote switch administration. Any additional SVIs must be created by the admin. They are created with the first time the VLAN interface is entered on a particular VLAN's interface. Enter the interface VLAN 10 command, for example, to create a switch virtual interface named VLAN 10. The VLAN number used corresponds to the VLAN tag associated with an 802.1q trunk. That becomes really important if you are using different types of equipment. At least 802.1q is standardized, so if I'm using VLAN 10 on this device, but I want to run that to, say, something wireless I've got, and I only want that wireless to see data on that VLAN, I can assign it. Or if I have a trunk and I want the wireless to have access to that trunk, I can do that. When an SVI is created, ensure the specific VLAN is present in the VLAN database. So the advantages of inter VLAN routing is that it's much faster than router on a stick. Router on a stick works and it's great, and I don't want to downgrade it, but it's slow because you're dependent on getting exactly half the speed out of the interface that you're sending the data out, because it's got to go out on the interface, go to the router, be routed, and come back. There's no need for external links from the switch to the router for routing, though you're going to have one link. You don't have to have many, and you don't have to set up all of these VLANs on it. It's not limited to one link. Layer 2 Ether channels can be used between switches to get more bandwidth. The latency is lower because it does not need to leave the switch to be routed. Anything you can keep on the fabric of a single switch is going to be faster, and this is one more way to keep things inside that fabric when possible. So a routed port is a physical port that acts similarly to an interface on a router. Routed ports are not associated with VLANs. Layer 2 protocols such as STP do not function on a routed interface. That's important to remember. Your spanning tree is not going to work on a routed interface. Routed ports on Cisco switch do not support sub-interfaces. To configure the routed port, the no switch port interface is used. Routed ports are not supported on the Catalyst 2960. So this is actually turning a switch into a router, because if you're going to actually have it as a routed port, you could route anything out at anything that's Ethernet. If you were part of a larger network, that was then out of your control, you could route out to it as long as you had IPs on both sides. The Cisco Switch Database Manager provides multiple templates for the 2960. 2960. I'm getting tongue-tied here. LAN-based routing is one of those templates that can be enabled to allow the switch to route between VLANs and support static routing. Use the show SDM prefer command to verify which template is in use. Get on Packet Tracer and play around with these. That's the only way to really understand them. The SDM template can be changed in the global configuration mode with the SDM prefer command. So things that happen. To troubleshoot layer 3 switching issues, verify the following. For VLANs, the VLANs must be defined across all the switches. The VLANs must be enabled on the trunk ports. The ports must be in the right VLANs. For switch virtual interfaces, SVIs must have a correct IP address. They must be up, so we got to make sure the no shutdown command. I know I say that all the time, but I tell y'all, when I was first starting to learn doing this stuff, that is the command I forgot the most. Out of all of the Cisco commands, I would forget to issue a no shutdown, so I was never turning that port on. And SVIs must match with the VLAN number. So troubleshooting layer 3 switching, verify that routing is enabled and that each interface should be added to the routing protocol. Make sure you're using the same protocol across them as well. Hosts must have the correct IP and subnet. Hosts must have a default gateway associated with a switch virtual interface or a routed port. So that is kind of a rundown of Chapter 5. We talked about inter-VLAN routing, the 3 types, legacy, router on a stick, and multi-layer switch inter-VLAN routing. Layer 3 switching, we talked a little bit about troubleshooting and some common errors.